So what we were doing was we were an astrobiology lab.
Okay.
So we were looking at how life came to be on the planet and
Oh,
why.
it's original.
Yeah, like very, very basic. So we're trying to recreate the primordial soup on this planet and see what kind of building blocks were in the primordial soup
Yeah.
and how life came to be from the primordial soup to what we are today. So in the lab, we postulated that the first form of life was going to be a molecule of RNA capable of self-replication and Darwinian evolution. And this was in Dr. Stephen Benner's lab at the University of Florida.
Okay.
And so one of the things we're looking at was meteorites. And meteorites, interstellar gas clouds. And
So you're talking human, you started from there, from the space.
From scratch. So we were trying to see how abiotically, so without life could arise on this planet.
Origin.
Yeah. So in interstellar gas clouds, you have building blocks like Lego blocks of formaldehyde, glycoaldehyde, and glyceraldehyde. Those are 1, 2, and 3 carbon building blocks.
Yes.
And we showed that when that comes onto the surface of the Earth, that can be mixed in when the Earth cools. So the Earth was molten, then it cools down to a level you can have some liquids, maybe not water because water boils at 100, but maybe something like formamide, which has a higher boiling point. And so you have these mixtures on the surface, and you have chemicals from space coming in onto the planet, and you'd form these pools, and you have mixtures of chemicals, and we showed that if you have formaldehyde, glycoaldehyde, glyceraldehyde with a little bit of base, that turns into sugars.
Okay.
And with certain minerals, you can guide which way the reaction goes. You can make certain sugars. And we were able to show that you could make biologically relevant sugars.
Sugar, which is carbon also.
Carbon also. So this is all, all CH2O, so
Okay.
all carbohydrates.
Okay.
So we were able to show that we can take 1, 2, and 3 carbon building blocks, formaldehyde, glycoaldehyde, glyceraldehyde, mixed with strong base and some minerals. You can actually make sugars from scratch. So the mineral here was boron. So boron was able to help us make 4 carbon and 5 carbon, 6 carbon sugars that were biologically relevant. So
that's how the creator of life.
Yeah, so if you look at a molecule of RNA, we were able to show that we could make biologically relevant sugars, 4 carbon, 5 carbon, 6 carbon sugars from scratch. And that's important because we were looking at, we were postulating that the first form of life on the planet was a molecule of RNA capable of self-replication and Darwinian evolution. And if you look at DNA or other biological polymers, it's an alternating sugar-phosphate backbone.
Okay.
And on the sugar, you'll have a heterocycle, which is what gives the DNA or RNA the letters A, T, G, C, or A, U, G, C.
The whole structure of the...
Of DNA. So when we were looking at meteorites and life on Earth, meteorites have many more building blocks for life that are made in these carbonation chondrites. Yeah. So you'll see many. So on Earth, we use about 20 amino acids for life. On meteorites, you'll find many more that we don't use here. And different kinds of sugars, different heterocycles that could be potential DNA bases. So the idea was that we had more complexity in this primordial soup, so maybe we had different letters for DNA, and what the lab was interested in doing was creating some of these new letters for DNA. And so back in late 80s, early 90s, my PI, Steve Benner, ended up making the first 2 new letters for DNA, iso-C and iso-G.
Okay.
And those ended up, so he created the first 2 new letters, so it's a 6-letter genetic code instead of a 4-letter genetic code. So you're already starting to expand the genetic alphabet. And so that's kind of like, so that ended up being used in products for DNA sandwich assays that were then used for detecting viruses in blood, for example.
Using that as a what they call a standard to measure all the DNA.
Other DNA. So that ended up being the most sensitive test for, it was called Versant, that was licensed to Bayer, now owned by, I believe, Siemens. It was the most sensitive test for HIV and hepatitis.
Okay.
But if you need to look for anything biological, you just look for a sequence of that the genetics of whatever you're looking for, bacteria or virus or what have you.
Like what we have now, even the COVID, you're also looking through that mRNA.
Correct. So in 2003, I believe, I was in his office at around 8:16 p.m. at night, I think it was the time, and he got an email from the National Institutes of Health, and then they had a new virus. They needed to detect it. They needed a test made, and so we sat together, and within about 45 minutes, we found a sequence of 16 letters of that new virus that was unique to that particular genome that was presented to us from the NIH, and then we put it into the databases and we blasted it to make sure it was unique to it, and had a test, and he sent it off to his company in Madison, Wisconsin, and they created the test that was sent off to Singapore, Hong Kong for the SARS coronavirus.
Oh, that was a SARS originally.
2003, yeah, about 18 years ago.
So actually, it was come from your lab.
That was his technology that enabled that. These new letters, we were thinking this primordial soup, these RNA molecules were using more than A, T, G, and C. They probably had all these different letters.
Standard A, T, G, and C, yeah.
Yeah, standard A, T, G, and C became the most stable ones, and that's what we all use now in life.
Or the DNA case.
Yeah, but back then there was more complexity, there was more functionality, so we started making new letters. And so that's what my graduate research was making new letters for DNA. So the lab ended up creating things like X, K, Y, Z, P over the years.
But there are 26 alphabets. I think we'll finish very soon.
Well, we're at, I think the lab is at officially 12 letters now.
From the original.
And they've also evolved the enzymes, which are polymerases, which copy the DNA. They've also engineered those to understand the new letters
So in other words,
and copy
you
those
actually
too.
have artificial created DNA.
Artificially created DNA with new letters.
Oh.
And so I had an idea of, well, this is data.
Yes.
I mean, this is information. So what about the future of computing? We're looking at data of zeros and ones, and ATGC is our data.
Okay.
It's almost like our blockchain.
Yes.
I mean, we are all blockchains.
Yes, in a way.
In a way, back to our last common ancestor, whenever that was.
Natural blockchain.
Yeah, natural blockchain. Yeah.
I like the word natural. Yes. So we are actually blockchain machines.
Yeah, it's fascinating how now in silico we're replicating what life has done in the universe.
I mean, we're talking about noobs. Well, I'm having my dupes now. That's good. Okay, now continue. Yes.
Yeah. So fast forward a little bit, and I realized that if you have zeros and ones, there's all data in silicon is zeros and ones. What if you transferred that into DNA? So the initial thought was take A's and T's equal to 0, and G and C equals to 1.
Okay. So you actually break out from the original the 6 or 7 original, and then make it into 0 and 1s.
Well, if you just look at a sequence, so say you take a data file, a text file or a picture file, and you break and you look at the binary code that actually comes with that, then it's all zeros and ones.
Yes.
On a hard drive, for example,
definitely.
it's all black and white dots.
Yes.
It's all magnetic zeros and ones.
Yes.
So what if we changed those and converted them into letters? So anytime you had a 0, you put an A or a T, and anytime you had a 1, you put in a G or a C.
Okay.
And then you convert the number sequence, zeros and ones, into letters.
Yes. And
then you take that now sequence of letters and you can synthesize it into a DNA strand.
Oh, so that means at the end of the day, practically my DNA is being read as 1 and 0.
In the end, your DNA can be read as ones and zeros. Yeah.
So if that's 1 and 0, that like what our intention was to do is how we're gonna break this DNA into a blockchain. That means, as you know, in order to do it, every human being itself, be tested like what you're saying. But how are we able to do it? I know there are some sequence they are doing is trying to create more carbon, using the carbon as like a reader. So you pull the data into the skin, and then you read instead of going down to actually test your blood, or hair, we're actually using the blood to read the carbon structure, and then form like a barcode using our blood.
Read your own blood. Yeah.
Yes.
I mean, we're getting to a point that our sequencing is so fast. Like DNA sequencing technologies, it's getting so fast that we'll be able to do something like if you ever watched the movie Gattaca.
Which one?
Gattaca.
Okay.
They take their DNA right to a counter and they give them the sample, and within moments they get back a full sequence of their genome.
Okay.
And with current next-gen sequencing technologies, we're getting to a much cheaper genome and much quicker sequence.
Yeah,
for
because
a
I
genome.
know in order to prime the DNA, it takes time to do it. So how fast can we do it now?
Now, I mean, people are doing it within matters of officially days in the lab, but you can. There are ways to even be faster with that. It depends on technology and how you want it to be done.
Yeah.
If you want to do end-to-end reads, there's a company called Oxford Nanopore that does end-to-end reads without chopping up your DNA.
Yes.
But other sequencing technologies, they chop up your DNA and they put it into a machine and they sequence each strand and then they put it back together.
The stem cell, they're doing that way, right?
Sorry?
The stem cell formula, they were doing that way, the stem cells?
Stem cells are a little different. So stem cells, I mean, you can sequence you can sequence the stem cells. And then the stem cells, for example, have longer AT repeats at the end. When you chop up the DNA in some of these sequencing methods, you don't know how long that AT segment is.
That's why your life is.
Yeah, and the idea is so at the end of your chromosomes, you have these things called telomeres, and they open and close.
Yes.
They get shortened as your cells copy each other.
Yes,
They have to get opened and closed when they replicate the DNA, and that shortening is what the people believe is what aging is. The aging comes from that. So if you can pause that.
Trying to restart it, so they have another 30 more times to live longer.
Add more and onto that telomere chain. Perhaps you pause aging, or
reset. Well, that's what they're doing, trying to look at in probably using what we call umbilical blood from the own child to extend.
So this is where the idea of stem cell banking, so cord blood banking. So if you have a baby, you want to take, when you have the baby, you want to take the umbilical cord and take some cord blood or even the cord itself and bank it, put it into deep freeze, and take some of it and isolate it.
So you can leave it again.
So when the child gets older, then you can go back to that sequence, that's the original sequence, and then you can essentially reset the human or treat certain diseases, and then you get into regenerative technologies also there.
Yeah, that's what I wanted. So now we'll be looking at this DNA blockchain, that's what we are interested in. How do you think we can do the implementation, more like what you say in physical sense, how do you think we can implement it?
So the idea that was presented was to take the DNA for whatever DNA was being presented, and then you want to sequence that itself, and then
so you come up with
whatever
the
whatever that code would be.
Yes.
And then you could directly translate that into a 0 and 1 sequence.
So that means we just probably write an algorithm to encrypt it.
Yeah.
And
then after that.
And then for me, with that encryption, I actually put inside my NFT or it becomes a token.
You can do it that way, or you could even you could even have a text file of the DNA sequence, and then you can encrypt that, or you can have an image of that turns into.
Yes. So this is where I need your advice in helping us to look at this, because this is where we are doing on NFT, and because as our things are getting more sophisticated, and then like our dear friend Muhammad, he has his impression with him for 15, 16 years. Some of you have generations of this. They don't want to something like be taken or shown off, and then suddenly they lost the ownership or something. So things are getting more and more important, because I believe Muhammad won't mind doing that DNA inside, so that he knows that he owns that. Like somebody says owned by him, you feel very cheated, because technology robbed his identity. That's what he's worried about.
Yeah, so security in that sense is huge.